Hello.
Oh.
Getting everybody in. Oops. Awesome. Let's see. I'm going to start from the basics, okay? And we'll try to go through fairly quickly because, like I say, I'm going to assume that you guys have the mathematical skills that you need. And so we're not going to take too much time hovering around on that. All right? So here we go. You guys have all, have you seen the movie Despicable Me? The first one. Not the recent ones, the first one, the really, that was the best one, I think. They all did a fairly good job, but the first one, of course, is always the best. All right, do you remember who the bad guy was in Despicable Me?
It was the guy in the orange tracksuit, right?
Yeah, the guy in the orange tracksuit. You remember what his name was?
It was like Vector.
It was Vector. Yeah. And he actually makes a little joke about it when he meets Gru in the bank, right? The bank is his dad's bank. And when his dad calls him in, he's like, Victor, get in here. And Victor's like, it's not Victor, Dad, it's Vector. But anyway, when he introduces himself to Gru, he says, name's Vector, because I'm committing crimes with magnitude and direction. And I think that was probably officially the first dab ever in the history of the world. But yeah, so he that's what he said was his crime name, because he was committing crimes with magnitude and direction. And so that's all a vector is. A vector is a number or a measurement or a value for which there's both a direction and a magnitude, okay? When we're talking about things like cookies, we just say 5 cookies. That is not a vector because there's no direction there. That's just a scale, what we call a scalar number, okay? So a scalar number are the types of numbers that you're used to working with in algebra and pre-calc. For the most part, you use scalar numbers until you get into this vector thing, okay? So scalars just have magnitude. A vector is a quantity. It must have magnitude and direction. Okay, so for example, and this is going to be important because the way that we do mathematics with vectors is going to be different than the way that we add scalars. All right. For example, if I say that I walk 3 kilometers to the east, and then I walk 4 kilometers to the north, if I ask, how far am I from my starting point, how would you answer? How far am I from my starting point?
If you want to calculate the hypotenuse, it would be 5 kilometers away.
All right, so yeah. Yeah, good. So from the starting point, I'm 5 kilometers away. Okay, now I walked a total of 7 kilometers. But when we add it, when we consider those directions, then it starts to do some different things with the mathematics. All right. And so that's kind of what we're going to be looking at today is how does direction affect things? All right. So we're going to start off with this. We're going to say that vector A is 3 kilometers to the right and vector B is 4 kilometers north, right? And I can write those separately, but I can also add those together. I can go vector A plus vector B equals vector C. Okay, now vector C is the addition of A and B together, and it should start at the beginning and it should end at our final location. All right, so vector C is going to go something like this. Okay, and you'll notice Averett said, well, that's the hypotenuse in this situation. Yeah, because I gave you specifically east and north, which are at a right angle. Okay, notice that when we added these two together geometrically or visually, we added them head to tail, right? The head of the first vector, the head of the 3 kilometers was added to the tail of the 4 kilometers. And that's how we add vectors, we say geometrically, the visual representation of those vectors. But we want to be able to deal with these algebraically as well to be able to get some numbers. All right. Now, Averett already gave us the length of vector C, just doing simple Pythagorean theorem, a squared plus b squared equals c squared. And he said, well, that means it's 5 kilometers. Okay. But vector C is not just magnitude. It's not just a length. We need a direction there as well. So how am I going to get the direction of vector C? How could I describe that?
If you want to describe the direction of vector C, you can just do northeast.
Okay, I could say northeast, but is it actually directly northeast?
No, it's not. Because
if
it's
it was
more to the north than it is to the east.
That's right.
You want to find, you can say it's a certain degree from east, or it's a certain degree from north.
Okay, so I could say that I could get an angle there, right? So how do I get this angle in degrees? What's the math that I need there? Somebody besides Averett.
You use sin.
Okay, so which, you want to use sine?
Yeah.
Okay, awesome. So I can use sine because I have the opposite side and the hypotenuse, right? So I can go sine of my angle is equal to the opposite, which is 4, over the hypotenuse, which is 5. Now, in this case, the hypotenuse was an exact number, and that's okay. Generally speaking, we're probably going to want to use the 4 and the 3 just because those numbers haven't been rounded. You don't want to use numbers that have already been rounded because when you round and use those numbers, your final answer gets rounded even more. Okay, so generally we're going to use the 4 and the 3, so we'll have to use tangent. But in this situation, because the 5 is an exact value, we can go ahead and use that. All right. Somebody punch, actually, I would like everybody to punch that into your calculator. Make sure that we're all on the same page here. Find out what angle we get there. I want to make sure that everybody can get this angle, that we don't get an hour into class and somebody's still like, I don't know where these numbers are coming from. Which that's exactly what happened in my regular physics class. So everybody find it. What's the angle?
Mr. Bywater, would it not be inverse sine of 4/5?
You will need to do inverse sine, won't you?
It'd be
Yeah,
53.
I didn't do the algebra for you. I just wrote down the equation. You guys got to do the math. That's what I'm hoping, right? To get the sine, in order to get theta, you got to move sine to the other side. That's exactly right. So it's going to be theta equals inverse sine.
Yeah.
I got 53.13.
Yeah, what he said.
53.1.
Yeah.
Okay, somebody else besides Yusuf get that?
I got it too.
Got that also?
Same.
Okay, awesome. All right, so Averett said, well, we can say this is kind of north of east or east of north or something like that. So if we start at east, that's the horizontal, then I need to rotate up 53.1 degrees, right? That's what this angle is saying, that from east, I need to go 53.1 degrees north. So that's one way to do it. We can say at 53.1 degrees north, oh, that's not right, north of east. All right, so from east, we're going 53.1 degrees north of east. That's one way to say it. All right, and you may see that from time to time. Now, another way to do it, because this is going to get really annoying if we have to put the north of east, east of north, all that kind of stuff all the time. And so another way that is commonly done, I'm going to draw this up in the right-hand corner here, is that kind of like in math, we define the positive x-axis to be 0 degrees, and then we rotate around counterclockwise from there. Okay, and a lot of times we do this in math. We say that this is 0, and then that makes the vertical 90 degrees, and 180, and 270, right? And so as long as I start at the horizontal as being 0 and rotate from there, that's what my angle will be, 53.1 degrees. So I could just say 5 kilometers at 53.1 degrees, and that would be an acceptable answer. Now, we can also go the other direction around our coordinate plane there, but if you go clockwise, then we got to do negative numbers, right? So if I start at 0 and go this way, this would be negative 90. And then I could continue going around that way. This could be negative 180. This could be negative 270. Right? And so you can have negative numbers as well. You can go the other way around. All right. Questions so far? All right. Here's what I would like for us to do then. We're gonna take a short hiatus from this. I'm going to, let's see, I think the best way to do this, in the classroom, I'm gonna post right now a document which is called the Intro to Vectors Lab. Okay, which I would like for you guys to try. Now, while I'm getting this uploaded, you're gonna need one of a couple of things because you're gonna be drawing your own vectors, all right? So if you have graph paper at home, then that would be great. Use the graph paper. If you don't have graph paper, then you could use an iPad or your computer or something and just open up you know, a file, a PDF of graph paper, and you could draw on there. If you don't have either of those options, you can just use a plain piece of paper, but be very, very careful and use a ruler. All right. So I'm going to get this set up and sent out in the classroom. And I'd like for you guys to make sure that you have one of those things. I'll attach to it as well a PDF of some graph paper just in case that's helpful. Okay, so I'm gonna upload this right now. All right, if you go to your classroom now, it should be inside the Intro to Physics section of classwork. And it's just called the Intro to Vectors Lab. Okay, now let me share with you what I'd like for you to do. We just talked about most of the things that are in that things you should know before you begin. Okay, so I'd like for you just to start here with part 1 for the directions for Vector Addition Lab. All right, and go from step 1 up to step 10. Okay, just part 1 for now, and then we'll see what we get together. what it's going to have you do is it's going to have you take these cards down here. Now it says to cut them out. Don't worry about cutting them out because that's going to take time to print and things like that. Don't worry about that. This was designed for, use in a classroom. So the first thing you're going to do is you're going to draw the vectors start in alphabetical order. So there's, it looks like blue would be first. So you'll draw the blue vector first, 5 units at 90 degrees. And so you'll go 5 units at 90 degrees, so straight up. And then to the head of that, you'll add the next vector, which will be the brown one. Okay, 8 units at 180 degrees. We're all going to do it exactly the same. Okay, we're all going to follow exactly the same process. Okay, alphabetical order, blue, brown, green. Okay, head to tail, every single vector. And then when you get to the end, you're going to draw the resultant vector that starts where you started in the middle of your paper and ends where your last vector ended. All right, and hopefully we all get exactly the same thing. Okay, so I'm going to give you a few minutes to do that. Go ahead and work through it. When you're done, here in the participants window, give me a green check so that I know that you're done with that first, just set 1, part 1 here. All right. Any questions? All right. So obviously in set 1, we all did exactly the same thing. So we all got exactly the same results. Okay. What happened when you shuffled the colors around and did something completely different?
It went back on itself.
Okay, so sometimes it overlapped itself. Okay, great.
For me, I got the same X and Y. What was it called again? Sorry, I forgot the name. The X and Y
components?
Yeah.
Aria got the same X and Y components. That's messed up.
So did
Anybody-
I.
Yeah, I also.
You?
I got it too.
What? You should have all got the same thing when you redid it. If you didn't, then you maybe made a little bit of mistake somewhere. Okay, go back and double check it. Okay, but part of the point of this was to see that it doesn't matter what order you add the vectors in, it gives you the same result, right? It doesn't matter if I go right and then up, or if I go up and then right, I end in the same point. As long as I use the same exact vectors and I add them appropriately head to tail, it does not matter what order you do them in. Anybody get anything else from that? Obviously was the big part of it, but anything else that you found? It's okay to backtrack, add it together, you get exactly the same thing. Anything else? Okay, I'm all right with that. Okay, now the interesting thing to do, one of my regular physics students asked, well, did we end up with the same thing because of the vectors you chose to give us, or because you gave us horizontal and vertical and not different weird angles and things like that, which was a good question. And the answer is as long as you add vectors together appropriately, it doesn't matter what direction they're in, right? If you think about it, when we started, we took an X direction and a Y direction, and we added those together to give us a vector in kind of a different angular direction, not a nice angle, right? It was a 53.1 or something weird, right? So if all angular vectors can be made up of horizontal and vertical pieces, then it doesn't really matter what angle it's at or what direction it's in. You can always go back to those horizontal and vertical pieces, which will add together to give you the same thing that you would have in any order. Okay, so that's kind of a neat thing with vectors, and we're actually going to use that right now to help us add together vectors that are not horizontal and vertical. All right, so come with me now as I share my screen again. All right, so we're gonna look at a couple of vectors that are not horizontal and vertical. All right, we'll start with one. Let's say vector A is 5 centimeters at 90 degrees. Okay, and then we're going to say that vector B is 3 centimeters at, we'll go 150 degrees. All right. Now, the first thing we're going to do is we're going to draw this so that we can visualize it. But what I need you guys to understand before we draw it is that the drawing part is absolutely not necessary. You don't have to do this part of it. Okay, what I'm going to show you is an algebraic process that's going to allow us to do it without having to draw the big picture. And that's helpful when you have 4 or 5 vectors. It's unlikely that you're going to see 4 or 5 vectors added together, but 2 or 3 definitely is a common thing. And very rarely you can add together a 4th vector. A lot of times they are horizontal and vertical, but you will get other things in different angles. So let's say we got vector A, right, which goes up 5 centimeters at 90 degrees. So when I'm drawing it, there's my 5 centimeters upwards at 90 degrees. Okay, and now vector B, I'm going to do B in green. B in green is going to be at 150. So remember, 0 is this direction. So 150, 90 is straight up. So it's got to be past the 90. It's got to be over here, kind of in this direction. And it's going to be 3. Okay, so that one's 3. This one is 5, right? So this time when I add them together and get my resultant vector, right there, my vector C. This time I don't have a right triangle, right? The first time was nice because it was horizontal and vertical. It was a nice right triangle that we could use. This one is not, okay? Now, of course, one way to do this would be to use sine rule, cosine rule, all that more complex trig stuff, but it's not necessary, okay? What I want to show you now is how we can use the components, which you were kind of introduced to in the lab. How can we use those components in order to add these vectors together? All right, so the first thing that we're going to do, for those that like steps, step number 1 is to break each vector down into its components. All right, so I'm going to take vector A, which is straight up in the air at 5. Okay, so that was vector A. And I'm going to write it so that I have the vector A in the X direction and the vector A in the Y direction. So it's horizontal and vertical pieces. All right. Now, in this situation, because it's straight up, we don't have any horizontal pieces, right? The horizontal, the AX is going to be 0. All right. And the vertical part is going to have a length of 5. So if it's vertical or horizontal, it's pretty easy to break it down into its pieces, its components. But the second vector, vector B, we're now going to look at vector B, which remember was at 150 degrees. So if that's 0, 150 is going to be kind of up in this direction with a length of 3. I want to break it down into its horizontal and vertical pieces. All right. So I need to make horizontal and vertical pieces there. So the same thing is going up to the left is I'm going to do exactly the opposite of what we did in our first example today. In the first example, we took a horizontal and vertical to get a vector up at an angle. So now we're going to take a vector up at an angle and break it down into its vertical and horizontal pieces. All right. So we're going to take this vector 3 and it's going to turn into a horizontal piece like that, and a vertical piece like that. And so I've got vector B horizontal in the X direction, and I've got vector B vertical in the Y direction. Now, if I add vector B X and vector B Y, they give me vector B, right? I get that resultant vector of B. Now I need to find out what those pieces are. This being 150. So how am I going to find out what length vector bx and vector by need to have in order to give me vector b? How would I go about doing that?
Sine and cosine?
I'm going to use some sine and cosine, aren't I? I'm going to use some trig. So first thing, I'm going to get this angle over here, which subtract 150 from 180. That'll give me 30 degrees, right? And so now, yes, I can use sine and cosine in order to be able to get bx and by. First, I'm going to go ahead and I'm going to do, let's do bx. So bx is adjacent, and I have the hypotenuse. So that would be cosine, right? So katoa. So cosine of 30 is equal to the adjacent, which is bx, over the hypotenuse, which is 3. Multiply both sides by 3, and we should be able to get bx there. Can you guys find bx for me? Either use your calculator, or I know your computers and phones have calculators as well. Go ahead and work that out. Find bx for me.
I got 2.598, which I rounded to 2.6.
Okay, so, oops, I'm ahead of myself. So I hear 2.60 in 3 sig figs. I need some confirmations. Make sure we're doing it right. Make sure that you're all able to do that.
If the known value of a value measured is just 3, why would you have 3 significant figures when finding bx?
Good question. We probably wouldn't unless we assume that 3 is exact. And a lot of times they're going to ask us to assume that things are, if we don't have decimals or if they don't tell us about sig figs, we just say, okay, it's an exact number. And so if 3 is exact, then it actually has an infinite number of significant figures. Anybody else got 2.6 there?
Yeah, I got the same.
Yeah, a lot of people getting 2.6. All right, lovely. Okay, can we then get by? By, of course, is opposite over hypotenuse. So sine. Opposite over hypotenuse. This one I know because it's 30, 60, 90 triangle.
$1.5? Oh, sorry.
Yes. Very good, 1.5. Hopefully everybody else gets that. Now, one thing to always kind of be aware of when we're working with vectors, right, is that when we have the components, it's still a vector, right? Bx and by are still vectors, which means they still need a direction. But because bx is only horizontal, then the only direction it can be is either to the right or to the left. And so all we need is a positive or negative. We don't need to give a degree there. And so if it's to the right, we leave the number as positive. If it's to the left, we're going to use a negative there. All right. So same thing with the up and down. Up and down, we still need to show direction. Up is positive, down is negative, right? So in this scenario, the x value, the bx, needs to be negative, okay? Because it is going over to the left. So I'm going to put a negative on my 260 there. Now, some of you that are farther advanced in mathematics or just are really good at it, maybe not super advanced, but you're just good at math and you recognize things, you may notice that you would get negative 2.60 and 1.5 by doing sine and cosine of 150 degrees. Okay, and if you're comfortable with that, you're welcome to do that. Okay, the problem I usually come across teaching students is that they then struggle with the idea that there's not a right triangle there. How am I doing sine, cosine, and tangent with the hypotenuse and adjacent and opposite if I don't have a right triangle? Okay, well, that is a valid concern and one that we're not going to go into because that's a math question. Okay, so make sure that you pay attention to the directions. It's fine to turn it into a right triangle and it works that way as well. Okay, so we've broken everything down to its components. Any questions so far before we do step 2? Step 1 was break it into components. Everybody okay? All right, so step 2 is to add all the horizontal components together and add all the vertical components together. So it's like we're taking the cards and we're shuffling it up and we're doing all the vertical ones first to get the vertical final component. And then we're going to add all the horizontal ones together. We're going to do all those next to get the final horizontal component, right? So it's exactly like that lab that we just did, but we're looking at the cards differently. We first took the vectors broken up into horizontal, vertical, and now we're going to take all the horizontal cards and add them together. And then we're going to do all the vertical cards and add them together. And so that will give us, hopefully, our final horizontal and vertical pieces for C. So my horizontal, I see an AX, which is 0, and a BX, which is negative 2.6. So when I add those two together, I'm going to get a CX of negative 2.6. Okay, that's the final when I add all those horizontal pieces together. I'm going to do the same thing with the vertical pieces. I'm going to add the vertical pieces together. So I've got here an AY, which was a positive 5. And then I've got BY, which is 1.5. So that's just like in my original drawing here, taking the 5 and then adding the vertical piece of 3 right there, which is going to get me to the height that C is supposed to be at, right? And so I add those together and I get 6.50. Now, with the final components, the final horizontal component and the final vertical component, I can now add those together and that will give me vector C, right? So I can take my CX now, which is negative 2.6, so it's going to the left, and I can take my vertical final component there, which was 6.5, and I can add those together to get my final C vector. All right, so I'm going to give you guys a couple of minutes. I'd like for you to please give me the final answer for vector C. All right, so give vector C its final value there. All right, so being a vector, what does it need? Being a vector,
that it's going in.
it needs both a magnitude, a value, and a direction. All right, so go ahead. I'll give you 2 minutes. When you're done, I would like for you to type the answer into the chat, but don't push enter yet. Just type a number. So you're going to do something like this. You're going to go 5 centimeters at 45 degrees. Okay, now obviously that answer is not correct, but that's what you're going to type. But don't push enter yet. I want as many people as possible to be able to put an answer in before we push enter. All right, so you got 2 minutes.
Hey, does anybody know how to make your calculator give you the decimal instead of a fraction?
What calculator are you using?
I'm using the newer calculator.
Oof, no, I don't know that one.
Elena, go into mode.
Okay, where is mode?
I don't know, maybe there's not a mode button.
Actually, here, there's like
Where?
a F2D, this fraction to decimal.
Oh, that works.
Thanks, you.
Welcome.
There should be an option to do that permanently as well.
I don't know. Yeah, that's right. Six. 66.4. 7 centimeters at 56 point.
Elena, your mic is on.
Oh, sorry.
Thanks for the answers though.
All right, that should be good on time. Make sure that you got something typed into the chat there as far as you got. Don't push enter yet. I'll give you about 10 seconds to finish putting it in there. Okay, make sure you got an answer put in and let's push enter. Let's see what everybody got. Okay, so it looks like we got a good variety of different answers there. Variety is usually a good thing, but I would say that's not necessarily a good thing in this scenario. Let's see. So looks like the most common length is 7 centimeters. That seems about right. Hopefully you did Pythagorean theorem, right? This is just a squared plus b squared equals c squared. And so you should be able to do that, do the 2.6 squared and the 6.5 squared, and then push enter and then square root it. You should get something close to 7. If you're writing it in 3 sig figs, it looks like SEM got 7.007. So 3 sig figs would probably be 7.01. But I'm not sure what you guys got on your calculators for that when you put it together. All right, so the distance looks good. Looks like degree-wise, we've got some 68-ish, some 112-ish. So it looks like those are supplements of each other for the most part. 111, about 112. Very good, 68.2. All right, so we're getting really, really close there. The one thing I'm gonna point out is that if you do the trig, which is probably what you would have done, you probably did tangent is the best thing to do there, because those, the 6.5 and the 2.6 have only been rounded once, whereas the C is calculated from rounded numbers and rounded again. So it's probably best to use tangent there. And so if you go tangent of theta equals the opposite over the adjacent, I'm assuming that what you get when you do the inverse tangent is 68 degrees, or maybe 68.0 or something. Okay, I didn't do the calculation. You guys can get the exact numbers on your own. Maybe 68.2, it seems like, is the number of choice. Recognize that this is this number right here. Okay, but when we identify a direction, it has to be with respect to 0, which is over here, the positive x-axis. And so the direction has to be this angle right here. Okay, unless you want to say 68.2 north of west, I suppose that would probably work. It would probably be acceptable. But in this situation, the best thing probably to do would be to subtract 68.2 from 180 degrees, which is why a lot of people are getting that 112 in terms of 3 sig figs.
So it's negative 68.2 degrees?
Negative 68.2 would not work, because if I draw my graph, remember 0 starts here, negative 68.2 would be in this direction like this. And so negative 68.2 would be around here. Right? So it's in that direction. If you did 180, negative 180, and then added on another negative 68.2, that could work. So negative 248, is that right? 180 plus 68, yeah. Negative 248, that would work, because that starts at 0 and goes all the way around to that same location. You probably won't ever see that in an AP question, just because they like to use positive numbers, but it is acceptable as an answer. Cool. Everybody good? All right. You guys did a lot with vectors today. Congratulations. You got a lot done. If there aren't any other questions, I'm going to go ahead and post the homework, which is kind of a intro to vectors worksheet. There's some applications on there. And so on each of them, you're going to have to figure out how vectors and how adding head to tail apply to each situation. Take note that you don't have to draw it every time. You can just do what we did there at the end, break each piece up into components and add the components together, and that should give you the answer in most scenarios. Okay? Any questions before we go?
Does College Board care when you're communicating components if it's in, like, with the brackets and vector notation, or do they have to be like with a subscript?
Nope. Nope. You don't have to do that. The bracket thing. Yeah. Is that what they taught in pre-cal?
Yeah.
That's more of a math thing. Really, if it's a vector, you'll notice that up in the top left-hand corner, I put the actual arrow on there. For vectors that are not horizontal or vertical, you should put the arrow on top to show that it's a vector. In textbooks, you might see that it's just bolded. They'll make it extra dark and bold it. That also classifies for a vector. Lots of physics books do that. But if it's just components, it's only two-dimensional. And so you don't have to do any other notation other than the subscript of the X or the Y, and then show that it's either positive for right or up or negative for left and down. That's fine. Yep. In some ways, the vectors get a little bit more complex here, but in some ways we're trying to simplify it because it's really just a tool that we use to help us with the physics, as you'll see as we get into the real physics in the next couple of weeks. Okie doke. Any other questions? All right. Nice job today, guys. You did well. We got through a lot. We'll start some real physics motion next time.
Thank you very much. Have a good day.
Water.
Bye.
Why water?